This is radians, arc lengths, and sectors. Main thing I like to start with is just this idea of what a radian is. And so what we did in the class is we took Skittles and we lined them up. And I'm going to just take this and we'll do a little infinite cloner. And we'll pretend these are 7 Skittles. Here's 3, 4, 5. Oh, this is going to be so close. 6 and 7. That is incredible. That's the closest I've ever been. In fact, if I move some of these back, but it's going to be almost right on. And this shows the radius would be 7 circles or 7 Skittles. Now, because that's the radius, what we can do is we can take these Skittles and make a little band of them on a circle. So we're going to go here, and we'll go up here, go here, go here, and you can do this on a piece of paper or on your iPad. But what's neat about this is that we're going to, the time we get to the 7th one, we will have the exact same angle that we would ever have, no matter how big the circle is. As long as we took the radius and put that radius on the circle, we will always get 57.3 degrees. This is the angle for 1 radian, or if we use the word radius, 1 radius on the circle creates an angle of 1 radian. So the 3 things I like people to know about radians: number 1, 1 radian equals 57.3 degrees. Second thing is radians are angles made from radii line, I don't know how I want to write it that way, but stretched out on circle, creating 1 radian. Now the cool part though of this is if we did continue this, so my first one was 57.3, the next one will be 114.6, and then the next one will be whatever that is times 3, 171.9. Well, 171.9 is really irritating because it's almost 180, but it's not quite. And so if we count how many radians there are, here's 1 radian, here's 2 radians, here's 3 radians, 1 radius, 2 radius, 3 radius, and then there's a little bit more, and guess how much more it's going to be? Well, it's going to be 0.14159 of a radian. And so that brings me to my number 3, probably the most revealing part of a radian is it takes 3.14 ... or pi radii on circle to make 1/2 of a circle. And of course 2 pi to make a full circle. So take a while, maybe come back, watch this video a couple times, just the first few minutes. Make sure you understand what a radian is. It's a radius on a circle, it makes an angle. So we can use this to convert degrees to radians, and you'll see why in just a moment. 45 degrees is going to be a certain amount of radians. And the way we convert it is that we know that there's 180 degrees, 180 degrees in a half a circle, and that's the same as pi radians. So you're either going to multiply by 180 divided by pi, or you're going to multiply by pi over 180. Well, I don't like to memorize things more than I have to, and if you have a pi over 180, notice these degrees are going to cancel. And so this will be left with 45 pi over 180, which is the same as pi over 4. And I like to take my calculator, take the non-pi part, 45 divided by 180, and then hit math, and then hit frac, and that will give you the 1/4, and you slap that on times pi. Try that for this one. Negative 480 times pi over 180. Okay, and when you simplify that, it's going to be negative, let's see, what's that going to be? 8 pi over 3, I think. And now it's in radians. This is how many radii there are on the circle to get 48, 480. And we'll talk about negative in a few days. Then to do the other way, you have radians. All you're going to do is you want the pi's to cancel out. So put the pi's down here, 180 here, and then you'll just multiply it out. 7 times 180 all over 6. And now we're going to end up with degrees. The pi's, of course, canceled. And this is going to be, I think, 210 degrees, I believe. And you can figure that out for this. So anytime that you want to convert, it's either 180 over pi or pi over 180. Whatever causes the pi or the degrees to cancel. So why are we learning this? Well, the problem with degrees is degrees are made up, and degrees don't work for actual lengths or areas. So whenever you have something in degrees, you need to get rid of it if you're finding lengths or areas. So I have a picture of this guy pointing, but let's say his arm moved down to here, and his pointing was there, and you looked at this angle of 30 degrees. You could figure out how far his fingertip moved by using this formula. S is the distance on the circle that it moves. So it starts at the bottom here and moves up to the top. The radius, r equal 5, is going to make a difference on how far it is. We can still have an angle of 30, but if your radius is smaller, that arc length will be shorter. So we will be able to find this arc length. Let me show you where the formula comes from first. So a ratio is when you compare two things. You compare something like angle theta to how many radians in a circle, or in a full circle it was 2 pi. So this is part of a degree, this is the whole circle. We're going to set that equal to another ratio, which is the ratio of the length on the circle, the arc length, which is part of the arc length of the circle. And then if we go all the way around the circle, it'll be 2 pi r. Well, that cancels out nicely, the pi's and the 2's, and you're left with theta times r equal to s. And that is the arc length equation that we were trying to find. So the only thing I got to warn you about is when you find this arc length, the distance moving on the circle, you can't just take 5 meters times 30. It'll be wrong because degrees are not made up. You can't use degrees. So we'll convert it into radians by multiplying by pi over 180. And that's going to be 5 times pi over 6, which is 5 pi over 6 meters. That will be my distance. Now in the second one, S equals R times theta, you have R as 5, and your angle is already in radians, so you can just go 3 pi over 5. Well, the 5's cancel here, so you get 3 pi meters for your arc length. So that's arc length, distance moved. If I'm actually making this an arc on the board, that length is your arc length. Now, if we're looking at someone making snow angels, like this, the area they make is called a sector. Or if you go to a restaurant, you don't order a slice of pie. A mathematician orders a sector of pie. So when you go to a restaurant, don't order a slice of pie, ask for a sector of pie, and you'll just be really respected by all those in the restaurant. Or made fun of. One of the two. So, same thing, we're going to set up a ratio, an angle, theta, part of the circle, compare it to 2 pi, which is all the way around. So this is the part, this is the whole. And then we're going to compare that to the area this time, the piece of pie, or the area of the sector. We're going to compare that to the whole area of the circle, pi r squared. So one ratio equal to another is called a proportion, and you can cancel out the pi's, but that's it. That's all you're going to get to cancel this time. You're going to have 1/2 times theta times r squared will be equal to area of a sector. And there's your area of a sector formula. Okay, so this example here, already in radians, area of a sector is going to be 1/2 r squared times theta, and then you have 1/2, 14 centimeters, got to square it, and then we'll multiply by 5 pi over 3. And you can simplify that all you want, but it's going to be square centimeters, and you can multiply that out. So for the homework, and here's some practice ones, convert to radians first. If you don't, it'll be wrong, because degrees are made up. And then a couple of other good examples here. I like those. And then homework is at the end. When you do the homework, check out, these are just some calculator converting to degrees, minutes, and seconds, changing back into decimal. Here's converting these radians into degrees, that's good. And then here's the most important part, you have S equal to R times theta, and you have A is equal to 1/2 r squared theta. Make sure that these are in what? Yes. And then you'll be fine. You can find those easily enough. And then this is a little Pi Day special question for you. What if you took a rope and tied it tightly around the equator of the Earth, tight as a drum? And then what if you added 10 feet? So you cut it here, and you added 10 feet. And then you stretched it out around the Earth equally. Somehow you hired people to equally separate it from the Earth. What is this distance going to be? So you started off with a string in purple that went around the Earth, snug as a drum, and then you cut it and added 10 feet and then equally pushed it out equally around the Earth, should be very difficult to do. What is this distance x? And since this is your only chance to see this, I will fill you in. It's either A, enough to slip a card through, B, enough to put your fingers under, or C, enough to crawl under. Well, which one seems the most ridiculous? Definitely C. But, as it turns out, it is the answer. And the reason it's the answer is that if you start with the circumference of the Earth, which is 2 pi, let's say the radius is r, okay? Capital R. And then you're going to, that's the circumference of the Earth, then you're going to add 10 feet, okay? So I'm just going to add 10 feet to this. Now what you're going to end up with is 2 pi r, but the new radius is going to be r plus x. So I'll say that one more time. You start with the purple, and you're going to add 10 feet. That's going to take the 2 pi, the radius is going to be x larger. Just a little bit, we don't know. Is it enough to slip a card through, enough to put your fingers through? Is it enough to crawl under? Well, what if it was enough to crawl under? Would you be amazed? 2, let's try this in yellow here. 2 pi r plus 10 is equal to, distribute this, 2 pi r plus 2 pi x. Ooh, that's interesting. The 2 pi r's cancel, and what you end up with is 10 is equal to 2 pi times x. X is 10 over 2 pi. Now, if you take your calculator, what's 10 divided by 6.28? Well, it's a little bit over a foot. And a foot is enough to crawl under. And it is C. So anyway, that's Radians, dealing with circles, and I hope you have a good story to share with someone.